Hey folks, Dr. Tom McNamara here again for our course in trigonometry. In our previous video we discussed the concept of a reference angle, and we're going to build on that in this video and show how we can use reference angles to help us with these inverse trig functions. We actually introduced these inverse trig functions earlier in the course, but I'll remind you of what they are here. So your trig functions, our first definition of trig functions in this course involved an angle in standard position. So your input was an angle. And your 6 trig functions gave you a rule for taking that angle and coming up with a ratio. We would take a point on the terminal side of the angle in standard position, and if we wanted to find, let's say, the cosine of our angle, we would take the x-coordinate of our point over the distance to the origin. It was x over r. So there was a rule for taking an angle and coming up with a ratio. The inverse trig functions go backwards. They take the ratio and tell you the angle that produced that ratio. Now we saw the usefulness of these inverse trig functions when we were solving right triangles. Okay, so remember, to solve a right triangle, we are supposed to identify all the side lengths and all the angles. Now let's say we had a right triangle, something like this, 3, 4, 5. The question is, what are these angles? Well, we can use an inverse trig function to figure out those angles. And just for the sake of completeness, I'll do an example right here. We know that cosine A is adjacent over hypotenuse, so cosine A equals 3 over 5. So to find angle A, I would use my inverse trig function, and I'm going to use my calculator to do that, so I'll do 3 over 5, and then second cosine, so approximately 53 degrees. And then I can find the other angle as well. Okay, so inverse trig function is very useful for doing stuff like that. The only problem is if we're talking about angles in standard position, which we're going to need to do when we talk about using trig functions to model periodic phenomena. If we're talking about angles in standard position, there are multiple angles that give us the same ratio. And let me explain why. There's one kind of obvious reason, there's one kind of not so obvious reason. Let's talk about a 30-degree angle in standard position. 30 degrees is a special angle. So we can work in a special triangle, or special 30, 60, 90 triangle. So if I want to find sine 30 degrees, I can get the exact value by using a special triangle. So sine 30 degrees is 1 over 2. Easy enough. Now, if we're talking about angles in standard position, well, this angle is coterminal with tons of other angles. Infinitely many other angles are coterminal with 30 degrees. One of them is 390. Right? I can go around a full revolution, and then an additional 30 degrees, I would end up in the same spot. So sine of 390 degrees is also 1/2. Furthermore, if I was over here in this quadrant and had that exact same triangle kind of mirror image, right, this point has coordinates radical 3 comma 1. This point right here, if I go just across the y-axis like that, well, the coordinates would be negative radical 3, y-coordinate would still be 1. Make that our 30-degree angle, that's our 60-degree angle. Okay. Well, if I look at this angle, this one going right here, okay, that is 30 degrees less than going all the way there. So this is a 150-degree angle. Sine of 150 is also 1/2. So the question becomes, if I told you I took an angle and I figured out its sine and I got 1/2, what angle did I start with? Well, there's tons of possibilities. There's a first quadrant angle, and 30 degrees is what your calculator will give you. That's what we call the principal angle. But we also have to realize there's a second quadrant angle that would also do it. And any angle that's coterminal with either of these is also a possibility. So typically, we'll need a little more information to nail things down. Let me give you a quick example here. So wipe my board clean. And let's look at this problem here. Find theta, find the angle theta to the nearest degree if cosine theta is equal to negative 0.8910 and theta is in Q2. Okay, so we are dealing with a quadrant 2 angle. Now, I'm going to start out by using my calculator here. So I'm going to take the cosine inverse of this number, negative 0.8910. So 0.8910, make it negative. Second, cosine, I'm going to take the inverse cosine. Okay, well that's convenient. My calculator just spits it right out. Negative 152 degrees. Okay, easy enough. Okay, now, anything coterminal with this theta would also work. Okay. Let's do another one here. Let's make it. Actually, let me change up the problem a little bit. Let me make it a Q3 angle. Okay, so theta is in Q3, and this is what I know about my angle. Okay, so one thing I want you to note here. In the first quadrant, cosine is positive, right? Because cosine is based on the x coordinate. So cosine positive, cosine negative, cosine negative, cosine positive. So your cosine inverse function will give you an angle that's either here or here. Okay, if your angle is positive, or if your ratio rather is positive, cosine inverse will put you here in the first quadrant. If your ratio is negative, cosine inverse will put you in the second quadrant. Now this problem is asking us for something in the third quadrant that would have this cosine. Now, the principal angle is 152 degrees. A lot of books call this theta hat, letting us know it's not really the answer we need, because this is not a Q3 angle, this is a Q2 angle. All right. So here's what I'm looking at. I recommend you handle it like this, draw yourself pictures like this. Okay. So, we got 152 degrees. It wouldn't go past this, right, because that's 180. So we're going through 90, 152 is somewhere about in there. Let's think about how much we have left right here to get to 180 from 152. That is 28 degrees left. All right? Now we want to keep the same cosine. That means we want to keep the same x-coordinate. Okay, so we kind of want to keep that the same, like this right here. So we're going to need to make that 28 degrees as well. Okay, so if this reference angle is 28 degrees and we want to be in Q3, we use the same reference angle in Q3. All right, so that's 180 plus 28 degrees, 208. 208 degrees. So this is the Q3 angle meeting this condition. Okay, I want to do a couple more examples. Two more. Okay. Find theta in Q3 with sine theta equals negative radical 3 over 2. Okay, now for this one they've given me an exact value here. Okay, so sine is equal to root 3 over 2. Now if I'm looking at sine, that should have come from opposite over hypotenuse. So I should be focused right here on this angle. Now, if this is my radical 3, this is the 30. Remember, in our 30, 60, 90 triangle, which is the special triangle that has the radical 3, the radical 3 goes adjacent to the 30, so that must mean we're opposite the 60. There's the 1, there's the 2. Okay, so the 60 degrees is my reference angle. The statement of the problem tells me that I'm in Q3. So I'm going to set up an angle in Q3 with a 60-degree reference angle. Now keep in mind, that is my actual angle going from here. My reference angle is going from the nearest part of the x-axis. If I'm in Q3, the nearest part of the x-axis is this one right here. Okay, so my setup would look like this. There's the 2, radical 3, there's the 1. If I were to look at this point, it would be negative 1 comma negative radical 3. And sine is y over r. Okay, going back to the definition of the trig functions as angles in standard position. So if I get a 60-degree reference angle and I'm in Q3, well, I got to go 180 to even get to Q3 and then 60 more. Okay? So this is really theta hat, right? My reference angle was 60 degrees. So theta would be 180 plus 60, 240 degrees. 240 degrees is the quadrant 3 angle with this sine. Now, technically, I suppose I could always add a multiple of 360 to this, okay? As the problem is written, any angle coterminal with 240 would do the job. Okay, one more. Let's do some of the other trig functions here. So we're going to find theta such that we're in Q4 so that secant theta is equal to 1.3054. So, I want a quadrant 4 angle such that the secant of my angle is 1.3054. Now on my calculator, I can figure out inverse sine, inverse cosine, inverse tangent. I cannot figure out inverse secant. But we know that secant is related to cosine. Secant theta is the reciprocal of cosine, going back to material that we covered in the first week, the reciprocal identities. So, the reciprocal relationship is symmetric, so if that's true, that means that cosine theta would be 1 over secant theta. If they tell me secant theta is this, I can use my calculator and figure out the reciprocal. So I put in the 1.3054, and this calculator has a reciprocal button, 1 over x. Okay, so 0.7760 to 4 significant figures. Guess maybe we could take 5. Okay. So, now if I use my calculator at this point, if I take cosine inverse of the number that I just computed, this thing right here, I'm getting 40 degrees. Okay, now, the question is, have I answered the problem? Am I done? Or is this just the reference angle that we're looking for? Well, this is looking for a quadrant 4 angle. 40 degrees would be a quadrant 1 angle. Okay, so this must be the reference angle, so I'll put a hat on that, letting everybody know that that's not really the answer I need. That's just the reference angle. If I'm in Q4, that's over here, a reference angle of 40 degrees would be looking like that. So the actual angle that I'm dealing with is 320 degrees. So reference angle of 40 degrees in Q4, theta equals 320 degrees. Okay, you can always check your work on these inverse trig functions, very easy to do. I just find the secant of this thing and figure out if the secant of my angle is equal to 1.3054. So I'm going to take 320, I'm going to take the cosine of that, do the reciprocal, 1.3054. Okay, great. So we have found the angle. Okay, so remember, if you're dealing with these angles in standard position using the inverse trig functions, your calculator will be telling you the reference angle. Sometimes that's all you need. Okay, if you look at that first problem before I modified it, we were looking for a Q2 angle, and my calculator gave me a Q2 angle. Here, I'm looking for a Q4 angle. My calculator gave me a quadrant 1 angle. Okay, so I needed to do a little bit of extra work there. So you may need to incorporate those ideas of reference angles that we talked about in the last video when you're working with these inverse trig functions.